Duh. Oh, hello there. Now, I'm not saying it's electromagnetism all the way down, but I don't know. Is it electromagnetism all the way down? We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one Ruliad. I don't think it rules them all. And it might be just hyper Rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here. Alright, what the heck is this dude talking about? He's showing this crazy thing with the magnet and the iron filings and mu naught. Okay, what the heck am I talking about? Alright. So as we can see here, was our standard thing. You got the magnet here, your little bar magnet. You got the iron filings. They seem to be going around a very particular way. Oh, very fascinating. Okay, today we're going to be talking about vacuum magnetic permeability, aka the magnetic constant, aka mu naught. Alright, so what am I talking about here? So as far as vacuum permeability, if you type it in and you go to the Wikipedia, take it for what it's worth. The vacuum magnetic permeability, variously a vacuum permeability, permeability of free space, permeability of vacuum, also known as the magnetic constant, is the magnetic permeability in a classical vacuum. In a physics, it is a physics constant, conventionally written as mu naught, or mu zero. Its purpose is to quantify the strength of the magnetic field emitted by an electric current. Expressed in terms of SI-based units, the coherent system of units we utilize, it is a unit of kilograms, meters per second to the negative 2 times amperes to the negative 2. Totally not confusing at all. Note, since the redefinition of SI units in 2019, when the values of E and H were fixed as defined quantities. Oh, it's the electron, electric charge, and H. Oh, that's Planck's constant, ain't it? Oh, something like that. Mu naught is an experimentally determined constant. Its value being proportional to the dimensionless fine structure constant. Oh, that's that whole 1 over 137-ish thingy. Yeah, which is known to a relative uncertainty. Oh. AKA, we're still not sure. Yeah, so, long story short, basically they've changed it. Here. The deviation of the recommended value from the former defined value is statistically significant at about 3.6 sigma. Just note that for a moment. Okay. So, what do we have here? Here's basically the number that we're looking for. This is from NIST. So we're looking here. We got vacuum magnetic permeability, or mu naught, numerical value 1.25663706212 times 10 to the negative 6 with error bars. 19 there, times 10 to the negative 6. Alright, that's cool. Now, what is the claim we're talking about here? The claim that we're talking about here is, hey, welcome Whitechapel. And welcome Jack's Law. We're going to be getting nerdy. I think you're going to like tomorrow. I'm just saying if we get there, things will probably make a lot more sense, because I had my questions. I still have some questions, but I think we're getting there. Okay. Got those things here. Alright, oh, boom. Alright. What is this crazy equation that Memes is bringing up on the board? This, and the reason I'm bringing it up, because, full disclosure, there's deviation from this number to that number. You can totally see it at, what is it, 6, 7 decimals, 1, 2, 3, 4, 5, 6. Oh, 7, there's an 8 there. 7, oh. Okay. So again, right around 7 decimal places, things get very interesting. Now, What is this equation? This is mu naught. Okay. So as we know, by utilizing the universal binomial factorization equation, basically it's our method of quantifying how different stuff do different things. I know, what a fascinating idea. So we have our primary action, and we multiply it by our boundary conditions. The dimensional ingredients, typically in Planck units, or perhaps like the mass of the proton, the mass of an electron. Basically, those are our boundary conditions. Then we multiply that by our terminal action over here, which is going to be 1 plus the action times the inversion boundary here. Oh, wait a second. These two things kind of look alike. Now again, I'm not saying that this makes sense on so many levels. It might make sense on a lot of levels. But, okay. So what is the actual thing that we have here? All right. So we got mu naught, we said, equal to 4 pi. Also, we could maybe interpret that as a sphere, if you would, assuming it's kind of like a three-dimensional force throughout free space. Is there any true free space? Is there any true vacuum? I don't know. And we multiply that by our boundary conditions, which for this is very interesting, because it's the same as our inversion boundary right there, which happens to be Planck length times the Planck mass, and that's all over the Planck charge squared. I know, charge, magnets. Imagine my shock. I made a funny. Oh God, some folks are cringing. It's okay, it's okay. We're plenty of cringe friendly here. Okay, so we got our sphere. We multiply it by the inversion boundary. And then we got our terminal action. That's 1 plus r squared divided by the square root of 2 pi. Huh. And then we multiply that by the inversion boundary. Okay, what the heck is r squared? So we go to our friend, the hyperbolic vortex equation here. Links are in the doobly-doo. Okay, so we got our standard 1 over x plus x cubed divided by 2 pi. And we set that equal to I raised to the I. And that's raised to the negative pi divided by 2. And we need a lambda here. What's our deviation? We subtract out the Planck mass boundary. Oh, very interesting. And we will go into at some point, God willing, all these extra digits and stuff and how we actually get there. It's a fascinating story. Okay, so I'm going to need to refresh this, but before we do, the whole reason why Thad was really big into this equation is before you add that in, he adjusted the algebra. Basically, it came out to the fine structure constant to about 7 significant digits, which that's pretty dang good. It was 2 orders of magnitude better than anything else he had ever seen for a geometric derivation. He's like, what do I need to set it to make it come out to be the fine structure constant to all the relatively uncontroversial numbers? This will be the Planck mass gap there. Very interesting. So we go to the first answer. The whole reason I'm doing this is because note, its value being proportional to the dimensionless fine structure constant, which is known to a relative uncertainty of about 1.5 times 10 to the negative 10. Okay, cool. All right. So, go back here. Oh, where are we? Here. Okay. So that was the first answer to the hyperbolic vortex equation. We probably don't even need those brackets. I know I don't need those brackets. We square that answer. Oh. 0.007299735252729 yada yada. Again, since it's a geometric derivation, you can go as far as you want. But, okay. And then I'll go to fine. Structure constant. Go! Wolfram alpha. Oh, what's this? 0.00 729735257. What do we have there? Oh. 257. All right. Hold on. Let me check myself. 35257. 35257. Oh. Looks like a geometric derivation of the fine structure constant, at least according to Wolfram Alpha. And there are experiments that will say this is not the fine structure constant. And there are plenty that would say, or at least suggest, this is the fine structure constant. I'll claim it is. Okay. We'll go back to here. Since we have the page reloaded, what the heck is this thingy here? This is Shoutout, like some of the doobly-doo. What this is, it's I believe, the third answer to the hyperbolic vortex equation in trigonometric form. So we take that number there, and then when we complete this action, we get Shoutout squared divided by the square root of 2 pi. Okay? So Shoutout squared divided by the square root of 2 pi comes out to be this number here. That's cool. Okay. And then we got our equation here. So we've got our 4 pi. And the interesting thing is, since it's multiplication, oh yes, this little inversion boundary. Remember, this little inversion boundary, again, Planck mass times the Planck length. No, Planck mass times the Planck length divided by the Planck charge squared. Okay. Comes out to be 10 to the negative 7. Very interesting. That's 7 significant digits there. Seems things kind of get a little hand wavy there. Okay. We go back here. So we got that. But we're also multiplying that by a terminal action here. Because we got a primary action. This is the boundary condition. Since it's multiplication, basically you can do divide by 10 to the 7th. Because it's 10 to the negative 7. So our boundary condition here for the inversion action is 1 plus Shoutout squared divided by the square root of 2 pi, and then another inversion right there. Comes out to be this number. Full disclosure, this is off. Again, it's based on the relative uncertainty of the fine structure constant, and we're getting down to very small levels of magnitude. So this number is 1.25. 1.25. 663. 663. 806. We're off again. Like I said, the data doesn't seem necessarily line up. And again, we've redefined it. And again, just slight note, since the redefinition of SI in 2019, the values of E and H were fixed as defined quantities. Each is an experimentally determined constant, value being proportional to the dimensionless fine structure constant, which is known to a relative uncertainty. The deviation from the recommended measured value and the former defined value is statistically significant at 3.6. Again, this is why we're conjecturing here. We have to be fair about these things. You know what, Jax? I really don't understand math. Wasn't really a math guy. I'm still not really a math guy. But all I'm saying is, I'm going to do a quote here. True love, priceless. For everything else is Wolfram Alpha. We go back to our friend Wolfram Alpha. So again, there is deviation here, but we're also off by, they changed it from about 3.6 sigma, which is interesting for something that we had, I believe, claimed to have known before. I'm just saying, where do we run into this issue? Okay. 1, 2, 3, 4, 5, 6. Oh, look, the 7th decimal place. How very fascinating. Now, again, there's a reason why this is actually at the top of the new chart here. That has technically the highest level of confidence in this. I brought up, I'm like, it's not lining up, what's going on here? Because again, it's like, I'm not a professionally trained physicist, I'm a dude on the internet. But all I know is, especially if we get into this tomorrow, rumor has it Big G may be stirring. I'm just saying, I'm gonna conjecture this is a geometric derivation of the magnetic constant. Now, this is why experiments are extremely important, and we need better precision experiments. Right? So we can figure out what's going on. Because now we actually have predictions. And I think that's a very fascinating thing. When something doesn't line up, at this point, it's like, all right, once we figure out other things, what may we be able to come to know within our realm of persistence? But that's all I got, man. So, hey, thank you all for watching. Peace out, everybody. It's a wacky and wild world out there. Take care of yourselves. Again, I think some really cool things are coming right around the corner. Peace out, everybody.
Have you guys checked out the Memes of Destruction's channel? He's an interesting dude. I like him.